Basically had the original reference pattern and we had to rotate it about 4 times. And we basically plotted it. I don't think I need to explain too much on this. Let's move on to how we rotate a matrix.
Okay, yeah, so just a quick comment on rotating matrices. So they can be expressed as a linear transformation, and like this is usually represented by a rotation matrix. However, we've sort of generalized this for any size. So it can be performed by multiplying by the anti-diagonal identity matrix as we've shown, and then taking the transpose of the resulting matrix, which can be expressed as the linear transformation shown at the bottom. And in practice, we just use np.rod90 throughout our computation.
So what multiplying by the anti-diagonal identity matrix does is it swaps like the first and nth row and the second and the n-1th row, and that's what enables you to rotate the matrix once you take the transpose. Okay.
We had questions on the matrix as well. We did it this way because it's a more generalizable solution and doesn't require specific rotation matrices for each dimension. So task 1b is to list the number of patterns, and this is basically just checking if each pattern in our array was equal to one of the 4 orientations.
And the reason you can just check for equality is because there's no noise. So every pattern is identical to one of the rotated versions of the master image. Okay, so for task 2, you're working with flattened matrices, which basically just means you take the rows and just append them to one another. So instead of a 36 by 36 matrix, you have a really long matrix. I can't do 36 squared in my head. And basically what you do to unflatten them is the procedure I just described in reverse. So you take the first 36 elements, and those are the 36 elements in the first row. You take the second 36 elements in the second row, etc., etc. In practice, we just use NumPy reshape because it's easier, but that's what it's doing. And then you just plot the same method as we described before. And then to list the number of reference patterns in each of the orientations, you rotate the reshaped image and then flatten it into each of the orientations, and then just check for equality again because there's no noise, so they're going to be exactly equal.
Okay, so task 3a was very similar. However, in that we were given a flattened matrix, however, we didn't know the dimensions of this one. So, but we knew its length was 1089. So you can consider the factor pairs of 1089. And we found that the 33 by 33 square matrix was the only one that returned a sensible image, as we've shown here. Okay, and task 3b was to list the number of each pattern in each of the rotations. So what we did was we unflattened the matrix, then performed the rotation, then reflattened, and then checked for direct equality again. And as there's no noise, we can simply do that. And then we just listed the number in each orientation.
Okay, so for task 4, you start getting noise in the patterns, which means they're no longer directly identical. So what the first task was to calculate the average pattern's total pixel value. Because we were given a design matrix, so a design matrix is just where each row is a flattened image, right? And so what we did is you just calculate the sum of all the elements in each row and then divide it by the number of rows, and that gives you 1251 as your average sum of all the pixels in each image. And then to render the average image, what you do is you take the average value for each pixel. This is assuming that all the images are the same orientation, by the way. You just take the average value for each pixel across all of the samples in your data set and plot that value that it gives you in that corresponding location in the matrix. So what this amounts to is you take the average of the columns in the design matrix and then plot the resulting row matrix after you've reshaped it. Okay, to plot each orientation class, what you do is you have to apply k-means, which is a heuristic unsupervised clustering algorithm, which we'll describe in a second. And this will return the 4 orientation classes, so we'll separate them out into those 4 orientation classes, and then you just plot the average image for each class like we just described.
I think all of you have heard about k-means on Monday, so I won't. I'll just speed through this. So we have like k-means plus initialization, which is where you choose 4 random points that are spaced far enough away as possible, and we assign them clusters, and we move the centroids so that they actually are at the mean of each cluster, and we reassign the clusters again based on Euclidean distance.
And then you just repeat this until like cluster membership changes become negligible.
Okay, so task 5A was, or task 5 was starting to look at probabilities that a matrix, or that the array was in a certain orientation given that you've got the resultant image. And because we're given the fact that all pixel values are independent, we can simply multiply the probabilities that it's at a rotation of 90 degrees, which was in task A, and we got the result there.
Yeah, and so basically what that matrix image on the left there is showing is the flattened 2 by 2 matrix after it's been rotated 90 degrees and the location of the outlier pixel.
Yeah, okay, so, and then task B was to express the ratio between the likelihood at that it was rotated 0 degrees and 90 degrees. So we had the rotation of 0 degrees as given in the question book, and then rotation at 90 degrees, and we just simplified the expression as follows. And then task C was to basically solve when this expression was equal to 1, and we found that beta was equal to 1 as shown. Okay, task D was in a similar situation, however this was expanded now to a 4 by 4 matrix rather than just a 2 by 2, and we found that the result is basically independent of the size of the matrix, and we sort of generalize this in a little bit.
And basically we've done the exact same procedure, except now there's just 16 squares instead of 4. So that's why it's the power of 15 instead of 3.
Okay, so part E was now considering the case where there's 3 outlier pixels rather than just 1, and however we see that as you rotate it 90 degrees, none of the outlier pixels lie on the same location as when they were rotated 0 degrees, so we can compute in a very similar fashion, and we find it's actually the same expression but now raised to the power of 3. Okay, and this was just a slight generalization of this statement. So we just said that if there's alpha outlier particles, and we also introduced another variable gamma, which represented the number of outlier pixels that would be in the same position after they were rotated 90 degrees. And we found that you end up with this very nice expression that's very similar to what you've seen earlier. And if we just basically plug in different values for alpha and gamma, we can find the same results as shown earlier in the task. Okay, now for 5F, we started to look at the log likelihood. So we start with the expression as given in the question, and because we don't actually particularly care where the outlier pixels are, we just basically decide that the first m pixels are going to be outliers, and the m plus 1 through to the nth pixels are not going to be outliers, so you're able to basically split it into 2 sums as we've shown. And so the first sum will have a mean of lambda, and then the second sum will have a mean of beta lambda. Okay, and then as beta and lambda are constant within the sum, we decided to break it up as shown. Yeah. And then basically we use the definition for the expected value of k, and because we also know that we're only calculating the average log likelihood, we can just say that k is going to be the expected value of k, and we end up with a simplified expression at the bottom, and we've also just plotted our result for, I think it was n is 90, m is 10, and in comparison with the expected result as given in the question.
Yeah, and basically the reason we can say that k is just going to be lambda is because on average k will be lambda, because there's a probability lambda that k will be 1, and a probability 1 minus lambda that'll be 0.
Okay, so task6a was using a sparse data format, although otherwise this was pretty much identical to 4. Task6a described which image A1 was in, and task6b described which pixel of that image had a 1, or otherwise task6a would describe which row of the design matrix we were looking at, and task6b would describe which column of the design matrix we were looking at. So, because they're both of equal shape, it didn't really matter whether or not we used the length of task6a or task6b to count the number of pixels with a 1, and divide that by the number of samples to find the average row sum. Task6b required us to reconstruct the design matrix first, using the rules that I set out earlier, and afterwards it was identical to 4b. 6c was also identical to 4c. And 7a. So initially we tried k-means like all of the other questions, and as we can see, it didn't really go so well. One of the clusters had a lot of the data points, and the other 3 clusters seemed to focus a lot on the outliers. As we can see, cluster 1 has a lot more data points than the other clusters, which only have a few thousand. This kind of indicates that the k-means didn't separate the data well, and that maybe this data wasn't very easy to separate. So some methods that we looked at to increase the separability of data include.
So we started by using a principal component analysis to reduce the dimensions that the data is in, because if you think about it, each image has 625 pixels, which means it's a vector with 625 dimensions, which means we're working in a 625 dimensional space. So in a very high dimensional space, Euclidean distance tends to be a less useful measure of similarity, which is what k-means uses to decide what's most similar. Because in those really high dimensional spaces, basically all the Euclidean distances are going to be really, really high because of that squared term in the Euclidean distance, so it tends to just blow up really fast. So we started by trying to reduce the dimensions of the data, and we did this using PCA, which kind of like maps that 625 dimensional data onto 25 dimensions in our case. So what PCA does is it tries to find like a vector u that minimizes the distance of each initial vector, which we've called x in this diagram, to its projection onto the vector u. So this is xi. That is, the vector u kind of represents the majority, like the direction in which there is the most variation in the data. And it does this for every single data point that you have. And these vectors u actually correspond to the eigenvectors of the eigenvectors with the highest eigenvalues of the covariance matrix. And the covariance matrix basically just describes the relationships between the variance in the variables you're working with, obviously. And so any eigenvector with a higher eigenvalue represents more of the variation in the data. And what we do then is we take the 25 eigenvectors with the 25 highest eigenvalues and let them kind of be our 25-dimensional axes onto which we're going to project all of our data. And that means that we now have our 625-dimensional data in 25 dimensions, and we've still preserved most of the interesting information, right? Most of the variance in the data, because anything that's constant, it doesn't really matter. And so that's how we reduce the dimensionality. And then applying k-means again gets you some pretty good separation between the clusters. So those are the 4 clusters, and this is our average image across all 4 clusters, which is kind of noisy, but a decent starting point.
But we weren't quite happy with it because that image contained quite a bit of noise. So here are some other solutions that we tried to maybe get a better separation. We had factor analysis, which includes some sort of dimensionality reduction before running something similar to k-means, although it didn't separate it as cleanly. This is possibly due to the clusters being too close, and also the problem with the really high dimensions earlier, and the noise.
Yeah, and the factor analysis, what it's basically trying to do is it's trying to find these latent variables that account for the variation in your data. And we thought, okay, well, we have 4 orientations, that might be our 4 latent variables, but obviously it didn't quite work out. We also tried a Gaussian mixture model of clustering, which is just another form of clustering which assumes that the data is composed of multiple Gaussian or normal distributions. This tends to work better on those less globular and more stringy clusters that k-means often fails at like separating properly. And what it does is it heuristically separates the data by initializing with a couple of means and standard deviations of normal distributions, and then assigning every data point to a normal distribution depending on how likely it is to be part of that normal distribution. And then you just, recompute the means, recompute the standard deviation, and repeat until convergence, pretty similar to k-means. But this is extremely sensitive to initial conditions. So we initialized it at the means that k-means found after PCA, and it still didn't separate the data properly, and also probably failed due to like a very high dimensionality of the data, which Gaussian distributions tend not to handle very well.
And we got asked what this tells us about the noise of the original image. And to be honest, we're not quite sure. We did some extra analysis on the image and found that most of the pixels followed this sort of normal distribution. So we're assuming the noise was normally distributed, but the Gaussian mixture model didn't separate them, likely for a lot of other reasons.
Yeah, probably due to the dimensionality.
So it turns out that the first solution that we tried still gave us the best image. But we still wanted to make it better, so.
We should also mention we did try using k-means with cosine similarity, but it failed for pretty much the same reasons as Euclidean distance. In high dimensions, it gets really, really big. Okay, so we developed an algorithm to try and use all of the data we had to create the clearest image possible and try and have more of the noise cancel itself out, because we thought some of the noise in our initial image was probably caused by miscategorizations of orientations, right? We thought that we probably put some, because of how noisy the patterns were and how sparse, we probably miscategorized some that were 90 degrees orientated as 0 degrees orientated. And so what we did was we took the candidate image we got from PCA and k-means as a starting point, and we took every pattern in the data set and rotated it until it was most similar by Euclidean distance to the candidate image we created through PCA and k-means. And we preserved the rotation with the greatest similarity and added it to a new data set. And we did this for all the images in the data set and then averaged them to create a new candidate image. And then we repeated this exact same process over and over and over again until the candidate images converged. That is, the candidate image stopped changing after each iteration, and this took about 30 iterations in total.
You can also think of this like k-means. So here, for example, is a 2x2 matrix, and all of those matrices on the left are the means that k-means has returned for us after being rotated to a common orientation. Because we can assume that all four clusters should be identical except for the fact that they're rotated, we can actually take the mean of these and then rotate them back out to get a more accurate or a more correct centroid for k-means to work. And then after that, we can reassign our clusters and recompute the centroids over and over again, and that can give us a more accurate image than just using k-means by itself.
And this is the code we use to do that, if anyone's interested. So it doesn't really,
so this process takes a really long time, and we've instead parallelized it to use as many of your CPU's cores as possible, and even then this still took 2.5 minutes. We also wrote a more optimized algorithm for it by skipping a lot of the steps while functionally still doing the same thing.
So it didn't seem like there was a huge difference at first, but when you put the two images side by side, you can see that we really did get quite a significant reduction in noise after we used that algorithm on it until convergence. And this was the final image we came up with for task 7. Still not entirely sure who it is. Best guesses at the moment are King Charles, but open to suggestions.
Yeah. And also we've included a really small version just so that the effect of pixelation doesn't get in the way of trying to guess who this person is. Otherwise that's it, right?
Yeah, that's pretty much it.
Thank you.
Thank you.